Section 1.1, graphs of equations, should be a review. If it's not, let me know and we can figure something out, but this should be a review. Equations are used to express the relationship between two quantities. So your first blank here, you want to write equations. You can do whatever works best for you in terms of taking notes with these videos. If you find that you'd rather watch the video and then go back and write your notes in, or pause it as you go, whatever works for you. This section will discuss the geometric pattern associated with an equation, or a graph. If an equation has the variables x, y, and the point a, b can be substituted in and satisfy the equation, then this point is called a solution point, meaning it makes the equation true. Most equations have infinitely many solution points, so the set of all the solutions is called the graph of the equation. Think about when you're graphing a line or any sort of function. If you're graphing an open-ended function, you're going to put arrows on the end, meaning it goes on for forever. It's infinite. There's infinitely many solutions to the equation. However, it does not mean that every single coordinate pair you plug in is going to work. It just means that for every x you plug in, there will be a y that goes with it. We're going to look later in the year at equations where this isn't the case. We'll talk about how they behave, why they behave like that, but that's later in the year. So here's a refresher. We're looking at a coordinate pair. It's an x and then a y. So it says determine whether the point 2, 13 and the point -1, -3 lie on the graph of y equals 10x minus 7. Here's what I'm going to do to determine whether or not this is the case. I'm going to take 213, and this is my x, this is my y. I'm going to plug it into my equation. So instead of an y, I'm going to write 13. Instead of an x, I'm going to write a 2. And then I'm going to decide whether or not it's true. I'm asking myself, is this the case? So I have 13 is equal to 20 minus 7. Yes, this ends up being true. 13 is equal to 13. This checks out. The point 2, 13 is a solution to the equation y equals 10x minus 7. Now let me try the same thing for -1, -3. When I do that, I realize -3 instead of the y is equal to 10 times -1 minus 7. I'm asking myself, is this the case? Is -3 equal to -10 minus 7? And I realize, no, -3 is not equal to -17. This is not a solution. If I was going to graph this, it looks something like this. -1, -3 would not fall on it, but 2, 13 would fall on the graph. That's all that I'm saying here. Here's some review of how to sketch a basic graph. Rewrite the equation to isolate one variable. So when we're talking linear equations, you're looking at y equals mx plus b, but you're also going to have other equations that aren't linear, meaning higher than an exponent of 1. And you're still going to want to do the same thing, because then you're going to make a table of values. By making it y equals, it's going to be easier to solve for your table of values. We're going to look at value tables that look like this. X, our work in the middle, and a y on the end. We're going to plot the points on an xy graph, and then we're going to connect the points with a smooth curve or line. So first example here is 3x plus y is equal to 6. Based on the steps we just talked about, I need to get it so that it's y equals. So I'm going to use an inverse operation and move 3x to the other side. So I'm looking at y is equal to -3x plus 6. If you're familiar with slope-intercept form, you could already graph this without coming up with an xy chart. However, for the sake of the steps, I'm going to do that. So I'm going to draw an xy chart here where I put my work in the middle. I'm plugging into this equation, and I'm going to pick one point to the left, the origin, and one point to the right of the origin. So I'm looking at -3 times -1 plus 6. -3 times -1 is 3, plus 6 leaves me with 9. -3 times 0 is 0, plus 6 leaves me with 6. And -3 times 1 is -3, plus 6 leaves me with 3. Here's another refresher for graphing. My vertical axis, meaning up and down, is my y-axis. The one that goes across, the horizontal, is my x. In the center is my origin. It's the point 0, 0. I'm going to plot the point. The x comes first, so I go to -1, and then I'm going to go up to 9, 3, 6, 9. I'm looking at the point 0, 6, 3, 6, and then I'm looking at the point 1, 3. Now I do the last step, which is connect the points with a straight line. Something people do, whatever works best for you if you're interested in keeping them organized, is make a straight line somewhere else on the page, sometimes draw the line as you go, and then use the scissor tool to pick up the line and move it onto the graph. As I was saying, if you have infinitely many solutions, you're going to show that by putting arrows on the end of your graph. That shows me this graph goes on for forever. There are infinitely many solutions. I can pick any x I want, plug it into the equation, and there will be a y that matches. Okay, my next equation is not linear. It's a quadratic equation. Degree 2, meaning an exponent of 2, is a quadratic equation. I'm expecting this graph to look like a parabola or a U-shape. We're going to learn how to look at these equations as they are and graph these without having an XY chart. But for now, we already have it as y equals, so I am going to create an XY chart to go with it. And I'm going to pick the same points just because they're easy to use, and one's in the left and one's in the right. So -1 squared minus 2, I'm going to do 0 squared minus 2, and 1 squared minus 2. -1 squared is actually 1, minus 2 is -1. 0 minus -2, and 1 minus 2 is -1. So again, I draw my y-axis, I draw my x-axis, my first point that I'm going to plot is -1, -1. I point the plot 0, -2, and I point the plot 1, -1. If you're going to use a scale of 1 on your graph, you don't need to label all of these like this. If you're going to use a different scale, so go by 2s, go by 3s, go by 10s, then you need to label. If it's not labeled, I just assume that you're going by 1s. I'm going to connect this with a smooth rounded curve, so it's going to look like, it's going to look like this. That's using my past knowledge, or now your knowledge, that a parabola is U-shaped. So that's a parabola, it's a quadratic. In my last example here, 2x minus 5y is equal to 6. I need to get y by itself, create an xy chart, plot my points, and then I'm going to look at connecting them. So just by looking at this, I know it's going to be a line because my exponent on my x is a 1. This is a linear equation. Instead of moving the x to the other side, here I'm going to move the y because the y is negative. So I'm going to try and get a positive y. So I'll have 2x is equal to 5y plus 6. I still need to get that 6 on the other side, so I subtract 6. 2x minus 6 is equal to 5y. I need to isolate the y, so I divide each piece by 5. I'm left with 2/5 x minus 6/5 is equal to y. That is my graph. Now I'm going to make an XY chart. This is going to get a little messy because we're looking at fractions here. So I'm looking at 2/5 x minus 6/5. I'm going to use -1, 0, and 1. 2/5 times -1 minus 6/5. Luckily, we already have a common denominator, so -2/5 minus 6/5 is -8/5. 2/5 times 0 minus 6/5 leaves me with -6/5. And then 2/5 times 1 minus 6/5 leaves me with -4/5. I'm going to go to my graph. I'm going to tailor my window to what I'm looking at. I know that my y's are all going to be negative. Right now I'm looking at really tiny values, they're fractional values, right? I'm going to make my graph a little different. So this is what I'm talking about if you're going to use a different value system on your x's and y's, a different scale. So instead of going by 1s, I'm going to go 1, 2, 3, 4, 5, and this is going to be 1. 1, 2, 3, 4, 5, and this is going to be 2, because then really this is negative 1/5, right? There's 5 of those. This is negative 5/5, which is the same thing as negative 1. I'm just basically zooming in on the window so I have a better idea of what I'm looking at. And on the top, I'll do the same thing, 1, 2, 3, 4, 5, although you don't always have to be consistent in your X's and Y intervals matching. I'm going to here just because I'm graphing 3 points. So 1, 2, 3, 4, 5. So let me say that again. On your x-axis, the intervals should match. I shouldn't have 5 be negative 1, but over here only 3 be 1. They should be consistent on the axis. However, I don't have to have my x-axis, and that's only 4. My x-axis match my y-axis. 1, 2, 3, 4. If I wanted, I could go by 10s on my y-axis and 1s on my x-axis, whatever is better suited for the graph, or best suited for the graph. So I'm going to start with the point negative 1, negative 5, negative 8/5. So 5, 6, 7, 8, and it's at negative 1. At 0, I'm looking at negative 6/5, which is right here, and at 1, I'm looking at negative 4/5, which is right there. I'm going to draw a line right here, use the scissor tool to pick up this line, stretch it to fit my graph, and go through all 3 of my points, put arrows on the end, and that is my graph. Again, if you already are familiar with slope-intercept form, you don't need to use an XY chart. However, you should show your work of how you got it into slope-intercept form. This really should be a review. If you need additional graphing practice, let me know.